designed for Zoom, not the room. So we don't have a great sound. So Dr. Larson has said he's got a good professorial voice, so I'll do my best to be heard. Back row, can I?
Or you could go home and watch it on Zoom. Right?
So, yeah, if anybody in the back row wants to raise their hand if you can't hear me or Dr. Larson, feel free to make sure everyone can hear me. Just a couple of quick announcements, and thanks to the Sisters Science Club board. There's the people running around with these little badges on, and Ann Richardson back there for taking our, the donations on the entrance. Also, the Sisters Fire Hall. I don't think there's any representatives of the fire hall, but if you see a fireman around, I guess thank him for the use of this place. Restrooms are back through that corridor. The men's is right there, and the women you have to go around the corner. If you've got a water bottle and you want to fill it up, you're welcome to use the kitchen over in that corner. Quick announcement about our Frontiers in Science series starting in the fall. It's going to be a change. We're moving to the third Tuesday of the month as opposed to the fourth as it's been for scheduling conflict reasons. But you'll get the usual announcements and plenty of warning about when the talks are. We're joined tonight too by the Sisters Astronomy Club. Jim Hammond is over at the table there. He can tell you all about upcoming events, including the Dark Sky Party that's scheduled for July 25th. So see him for more on that. Also, Dr. Larson, I'll be introducing him in a moment, but he's also speaking tomorrow night in McMinnville and Friday night in Sun River. Tomorrow's topic's wormholes and Friday is quasars, so if you don't get enough tonight, why hit the road and you can follow him around on his tour. So our speaker tonight's Dr. Shane Larson. He is a professor of physics at Clarkson University, and I'm sure he's going to be asking anybody here have a connection to that university, but he's Director of Integrated Engineering and Applied Science Projects at the Coulter School of Engineering and Applied Sciences, affiliated with the university. He works in the field of gravitational wave astrophysics. He specializes in studies of compact stars, binaries, and the galaxy with both the ground-based LIGO and the forthcoming space-based observatory, LISA. I think we'll be hearing more about those tonight. And he's currently a member of the board of the International LISA Consortium and co-chair of the LISA Astrophysics Working Group. He grew up in Eastern Oregon in La Grande. He has a BS in physics from Oregon State. His master's and PhD are from Montana State. Postdoctoral work at JPL, Caltech, and Physics Frontier Center at Penn State University. He's an award-winning teacher and a fellow of the American Physical Society. Let's welcome Dr. Shane Larson.
So I teach intro physics and astronomy, so they put me in the big lecture hall all the time, and when the microphones don't work, I have to yell. So I'll do that now. So I've been, those of you who know me, I've been to Sisters many times. I'm connected to Jim and the amateur astronomers, and I know several others, Mel and other folks from my time here in the Pacific Northwest. But every now and then, I come back and things have changed, and so I've been at Northwestern for the last 15 years. And we just moved to northern New York. Northwestern's in Chicago, and northern New York, where we are, is right outside the Adirondack Park. So the thing that has changed the most for me is my skies are very dark now. So I can use my telescope, and I can do astronomy in northern New York. We're right outside the Adirondack Park. Any Golden Knights in the audience? Any Clarkson alum? Every now and then there's a few of them. Yeah, okay. So we're a small private technical university, so we got about 5,000 students. We generate lots of engineers and scientists and folks like that. So every now and then there's someone in the audience who's like, hey! Oh, okay, you're everywhere. So I work in gravitational wave astronomy, and actually we need to put my laptop in place. So actually I should have done that before, so I'll do that while I'm chatting with you. I do work on both LIGO and LISA. And so last year when I was here, I talked about the frontiers of astronomy. So astronomy is in a revolution right now, and those of you who pay attention have probably heard this. The technology is changing rapidly. The telescopes and their capabilities are changing dramatically, not only in terms of traditional astronomy using telescopes, but also in terms of different kinds of ways of looking at the universe. And so what we're going to talk about tonight, gravitational wave astronomy, is one of those different ways of looking at the universe. Rock and roll, look at that. Okay. Last year when we talked about the frontiers of astronomy, I mentioned some of this. We talked very briefly about it at the end. But when we were talking about what to chat about this year, when I got the invitation, thank you Science Club and Jim for organizing all that, we said let's do the full gravitational wave talk. Okay? So how many of you have heard about gravitational waves before? Okay, how many of you have been to LIGO here in the Pacific Northwest? Oh, a few of you. Okay, good. Okay. So mostly what I'm going to do tonight is I'll do a little bit of intro about gravitational waves, what they are, how we think about them, and then I'm going to tell you mostly about LIGO. There have been tremendous discoveries made in the last 10 years, and I'm going to kind of tell you about the 3 that I think are most important. If you go grab a different LIGO person, they're going to tell you about 3 other ones that they think are important, okay? But I'm going to tell you about the 3 that I think are most important because they really kind of define the kind of transformative way that gravitational waves is changing astronomy today, okay? Mostly by showing us things that we didn't have any idea what was going on before we discovered them, okay? So that's the way I'm going to do it. As we go along, if you have questions, please ask. Okay, so raise your hand. If you're confused, almost certainly the person next to you is confused too and was too shy to ask a question. Okay, I'll try and control that so it doesn't suck up all our time. But what will happen is 2 weeks from now, you'll wake up at 2 in the morning and you'll have some question you wished you had asked me. Okay, and if you don't know it yet, you will discover then that your significant other does not want to talk about astrophysics. Okay, so when that happens, my email address is right here. That's Larson@clarkson.edu. If you send me an email, I'll do my best to find you something to read, something to watch on YouTube, to kind of give you some, or answer your question if I can. Okay, and at the end, those of you who've seen me give talks before, I always have extra stuff for you to go read. So there will be reading for you at the end. Okay? Okay, here's my blog, rightscience.wordpress.com. I've written a lot about gravitational waves there. It is a public-facing blog. It's mostly so my mom knows what I do. So my mom's a forester, so that will kind of give you a sense. You should be able to hopefully understand it. Okay? And you can certainly follow me on social media if you want to. Okay, so tonight, we're going to come back to this plot over and over again. This is a plot that we created at Northwestern. There's an interactive, so you can go change the way this plot is displayed and change the information on it. But it's a very nice plot for capturing what we are learning and what we're uncertain about and what gravitational waves is telling us. Okay, it's not a normal plot. It is a plot where along the vertical axis is plotted the mass of the object we're talking about. And tonight we're mostly going to talk about black holes. Okay, so you'll see they range there from 1 all the way up to 200. Okay, the horizontal dimension in this plot means absolutely nothing. Okay, so that's the thing that's different than normal plots. Okay, so if you go play with our widget, it'll let you change how things look horizontally, so you can put your own artistic flair on this plot to impress your friends at barbecues or whatever you use the plot for. Okay, so we'll come back to this over and over again, but this is what it looks like. Okay, and the title here is Masses in the Stellar Graveyard. Okay, what we're doing is we're probing the universe by looking at dead stars. Okay, so this is the game. Okay, oh, there's the URL. So if you go to that URL, it's interactive. You can change things and generate your own. Okay, and I'll show it again at the end. Okay, so let's talk about gravitational waves. So for most of human history, we've used light more than anything else to understand the universe. And we've done that not just as scientists, but also as amateurs, but we've done it so well that I can put up a picture like this, even among people who haven't studied astronomy, and they recognize many of the things in this picture, right? What's this at the top here? Oh yeah, it's the moon. How many of you have seen the moon through a telescope? Okay, good. What's this? Jupiter. How many of you have seen Jupiter through a telescope? Okay. What's this? How many of you have seen the red spot through a telescope? Yeah, okay, so the number's getting smaller, but you all know it's the freaking red spot, right? Okay. Saturn. What's this on the bottom of Saturn? It's the aurora on Saturn, right? Okay. Milky Way. You live in a place like Sisters, you can see the Milky Way. You live in Chicago, you cannot. You live in the Adirondacks, you can. It's great. I can see the Milky Way again. Okay, over here it gets harder. What's that on top? The Andromeda Galaxy. The most distant object you can see with your naked eye, the way we've done astronomy for 40,000 generations. Okay? But it's the closest galaxy to us that's like the Milky Way. We learned a lot about the Milky Way by looking at Andromeda, right? These things? Yeah, this is called the Bubble Nebula. What's this one called? The Veil Nebula. Okay, so this is part of our story tonight. These, we didn't know it when we first started discovering them, but these are part of the remnants of stars that have died. And so they're part of the story we're going to talk about. And this? Yeah, it's M13. I think it's M13. Yeah, it looks like it. Okay, so this is called a globular star cluster. These orbit the Milky Way. They have the oldest stars that we know of. Right? Okay? But no human has ever been farther than the moon. But you all know all of this. And how many professional astronomers in the audience? Okay, just me. Okay. But you all know all of this, right? And it's really a testament to the power that our civilization has to collect knowledge and distribute it to all of us. And we've done this for hundreds and hundreds and hundreds of years now. And it's only in the last 400 years that we've been doing it with technology and not with our naked eye. But you and I have lived in the future now, and now we harness technology to look at the universe, not with things that our bodies are capable of discerning, but with things that we have posited exist, and then we build experiments and we're like, whoa, we were right. These things exist. Okay? And so those things that exist are what we call gravitational waves. Now, there is a way that we think about this that anyone who's been trained in relativity is like, that's what gravitational waves are. I'm going to give you a different way of talking about it, that if you talk to your friends who are relativists, they will make faces with their eyebrows crinkle. Okay? But it's a useful way to think about what gravitational waves are. And so I want you to have it in your head as we talk about it so you can understand why this is a useful way for probing the universe. Okay? So, it goes like this. The thing that Einstein taught us is nothing can travel faster than the speed of light. Right? All the stuff that Einstein did related to relativity and all that, it boils down to that one statement. And he kind of intuited it because he could imagine situations where that was the only possible way experiments would make sense. And physicists are like, really? And then they go do the test and yeah, it seems to be true. Okay, so for 125 years, this, what then was a postulate, has experimentally been proven to be true. Okay, and so in particular, gravity cannot travel faster than the speed of light. Okay, so let's start there. Now, imagine my hand is a black hole. Okay, and if you go back to your high school physics class or your college astronomy class, and you learned about Newtonian gravity, the thing that you were told is that the gravity you feel depends on the mass of the object and how far away it is from you. So here's a black hole, and it's pulling on each one of your foreheads in a line straight towards that black hole. Okay? Now what if I have another black hole right here, right next to it? So now the gravity on your forehead is a little bit towards this black hole and a little bit towards this black hole. And it's pretty strong for these folks here in the front row. They're like, whoa, this is really hurting my head. Okay? And those of you in the back row, it's weaker because you're farther away. Okay? But what if the black holes are moving? What if they're orbiting around each other? So if one of them moves like this, now this black hole is pulling more strongly on your forehead. And this black hole is pulling more weakly on your forehead. And so what you feel on your forehead has to change. But nothing can travel faster than the speed of light. So as this happens, it takes time for that very interesting information to travel from these black holes to you. Okay? That's all gravitational waves really are. So Einstein thought of this in 1916. He did what all good physicists do. He got out, he did some calculation. He's like, yeah, we're never going to be able to detect that. Okay? And he gave up. Okay? And there were other debates swirling around this. People weren't sure they were real because, you know, who knows? And if we can't detect it, how are we ever going to prove they're real? Okay? But, as we just said, you and I live in the future. And we have lasers and computers and really precise measurement technology. And we have harnessed it, this is the story we're telling tonight, to measure these gravitational waves that travel from massive objects clear across the cosmos to here on Earth that have gone undetected for the 500,000 years that humans have been on the Earth. So you will see movies of this. This is a movie that I like to show. Okay, so this is two black holes going around each other. The lines in the color you see are the gravitational waves, so where the lines are bright is where the gravitational waves are strongest. And when I play the movie, you will see them moving away from the black holes, and you will see them changing as the black holes move around each other. Okay, and the reason I like this movie, the reason I like this movie is because if you look, you'll see the gravitational waves change dramatically. They encode all the structure of the black holes, and they propagate in every single direction, which is why it's useful for astronomy. It's just like a star. A star sheds light in every single direction. It doesn't matter where I am in the galaxy, I can see that star in my telescope and do astronomy. Same thing is true for gravitational waves. It doesn't matter where I am, those gravitational waves go in every direction, and so I can detect them and do astronomy. You will see other movies that look like gravitational waves that are ripples on a pond, and those are fine, but I like this movie better because it shows why we can do astronomy with it, because they go in every direction. Okay? Okay. Now, you may remember our questions. Everyone good? Okay, brains aren't melting yet. Good, that's good. Okay, so you may remember that light comes in a spectrum. Okay, if you never took physics, you're used to the rainbow that comes out of a prism or after a rainstorm, the colors of light that you can see, which are red, orange, yellow, green, blue, indigo, violet, the visible spectrum as we call it. Beyond that are types of light that our eye can't see. X-rays, radio waves, ultraviolet light, infrared light, gamma rays. We've learned to use all of those for astronomy. So as it turns out, gravitational waves also come in a variety of flavors, in a spectrum. Okay? And so what I've done here is I've drawn the gravitational wave spectrum out. There are some numbers on here for those of you who study spectrums or remember spectrums from school. They're kind of familiar numbers. The number that astronomers use to characterize gravitational waves is called the frequency. Okay, those of you who remember your physics class is related to something called the wavelength. We could have easily done this in terms of wavelength, but so astronomers tend to use wavelengths and frequencies and energies and temperatures and all kinds of different things. It's very confusing. Okay, gravitational wave astronomers are very practical, smart people. We all use frequency, right? So we know what we're talking about when we talk to each other. It makes it very easy. Okay, so these frequencies, what you'll see, this spectrum goes from a very small number, 10 to the minus 16, that's a 0, a decimal, 15 zeros, and a 1. So it's a very tiny number, all the way up to 10 to the 2, or 100. And it goes a little bit farther than that, into the thousands. Okay, so everywhere along here, there's a colored box, which is a place where you and I, being people of the future, have good technology that we're already using and working on to detect gravitational waves. Okay, and it's awesome because it took astronomers with telescopes like 150 years to cover their entire spectrum. And we're basically starting gravitational waves here at the turn of the 20th to the 21st century, and we're covering this huge swath of the spectrum. Down here at what we call low frequencies, okay, we are looking at the cosmic microwave background, which some of you may be familiar with from cosmology. Here at 10 to the minus 8, so that's about 1 to 10 nanohertz, as we say. We use a radio astronomy technique called pulsar timing. I'm not going to talk much about these two tonight. There was a big announcement about pulsar timing about a year ago, so if people want to talk about that, I can answer questions. And then over here, this is where all the action is right now. Okay? So this is on the ground. We're building large gravitational observatories. They're about 4 kilometers in size. Those of you who know the LIGO have probably seen these. And then in space, what I work on mostly, LISA, these are observatories that are millions of kilometers across. Okay? And they all use lasers to do their technology. Why are we covering the whole spectrum? Because if I sit down and I talk to every astronomer I can find and ask them, what sorts of interesting things would you like to learn about in the universe? And then I go figure out if those interesting things emit gravitational waves, what we find is there are gravitational waves that emit across the entire spectrum of all kinds of interesting things that we hear about when we talk about modern science and modern astronomy. And lots of them are known. There's maybe a couple of examples. Lots of them are mysterious, and there's lots of unknown questions. And it's just, we need better data in order to understand what they are. And so gravitational waves provides that. It's a new, unique, and different way of looking at the universe that will inform us about mysteries that we have long been trying to understand. Okay? And so over here, what you and I are going to talk about tonight, we're focused on this area of the spectrum. Largely our sources are what we call binaries. They are two astrophysical objects. Mostly we're going to talk about dead stars, black holes, neutron stars, white dwarfs. They're dead objects that orbit around each other. Okay? And that time that they orbit around each other is related to this frequency. So you see the top row there. Okay? That top row, it says period. Roughly speaking, we're talking about binaries that go around each other on the scales of hours, seconds, and milliseconds, thousandths of a second. Okay? So these are things the sizes of stars going around each other 1,000 times a second. Right? When Einstein was thinking about this, they didn't know about stuff like this. Right? So not only did he think it would be impossible, he didn't even know of anything that would emit gravitational waves at those frequencies. Because in those days, all they knew about were planets, stars, and moons. They didn't know about black holes and neutron stars and white dwarfs. Right? Okay, so if you're an experimentalist or an engineer, one of the great things about working in modern science is you can't just do it with astronomers and physicists. You need engineers, you need laser folks, you need computer scientists. Okay? And so if you're going to build an experiment, you have to know what you're going to measure. And then you go down the hall to your experimental colleagues and say, can you measure this? And they're like, yeah, no, we can't do that. Which is what Einstein did. But I went down the hall and my friends were like, oh yeah, that's easy, we can do that. Okay? So they spent $400 million and they can measure it, right? Okay, so this is the what should we call it? A Gedanken experiment, the thought experiment that shows how we're going to measure gravitational waves. So what I've done here is I've made an array of rocks. Okay? Little heavy things, doesn't matter what they are. Gravity affects massive things, so my detector is basically built of rocks, okay? Things that will respond to gravity. And so at each point on the grid, there's a little rock. Okay? Now when a gravitational wave propagates through that array of rocks, what we're going to do is measure what happens to the rocks to detect the gravitational wave. So imagine a gravitational wave propagating from the back of the room straight through the screen, into the screen, and out through the wall. Okay? What it will do to the rocks is the following. It will distort the separation between the rocks in a regular and repeating pattern. And what you'll see here, okay, so the center rock is our reference point, and as you go along, all the other rocks alternately move away from it and then back towards it. And in the horizontal direction, when they're moving away, in the vertical direction, they're moving towards. And then when they move away in the vertical direction, in the horizontal direction, they come in. So if you kind of have two rocks like this, they kind of do this kind of thing. Okay? Now, do you see what I'm doing? We call this the gravitational wave dance. And I want videos of all of you doing it at the bar tonight. Okay, so we call this plus. This is a plus polarized gravitational wave. Because if I draw the axes the distortions happen, they look like a plus sign from math. Okay? Now, there's another flavor of gravitational waves that happens at the same time. Okay? And it also produces a distortion, but it produces them along diagonal lines. And it's the same thing. It compresses and stretches, and then compresses and stretches. Okay? So we call this cross. Those of you who have maybe fond, maybe not fond memories of calculus, you probably learned about the cross product in calculus. It looks like an X. So we call this cross. Okay, so these are the two flavors of gravitational waves that get generated. Yes, sir?
How does it know in the middle?
That's a great question. How does it know where the middle is? It doesn't matter where the middle is. It matters which one you're using to measure everything against. So if you like, we're going to go out in your backyard and try and lay out where your fence goes, you put one post in first and you measure everything against that fence post. So that's what we do with our gravitational wave detectors. We pick one that's going to be our corner, if you want, and then the others we lay out in reference to it. So we just pick where it goes. And everything gets stretched relative to that point that never moves. Does that make sense?
Yeah.
Okay, that's a good question. Other questions? We'll come back to it. Okay. Okay, so this tells us how you and I are going to measure gravitational waves because we live in the future. I'm going to pick 3 rocks, as I just described to this gentleman here in the front row, and I'm going to shine lasers back and forth between those rocks to determine how far they move away from each other as the gravitational wave goes by. Okay? Now, do you want me to tell you the number that's going to melt your head now? Okay, so I'm going to tell you about the first detection we made. The first detection was made at LIGO. This is 4 kilometers from one rock to the other. Okay, and the difference, the change in length between those two was 10 to the minus 18 meters. Okay, so that's 1/1000th the diameter of a proton. Okay, so you take a meter, you divide it up into a trillion bits, and that's what we are capable of measuring now in the future. Okay? Lasers, which Einstein is the father of, right? He just didn't know. Okay.
But that difference could just be the width.
Okay, yeah, so this is a great question. So what else could cause that, right? So what else could cause it? So in experimental physics, we call that noise. Okay, now most of you, maybe not most of you, many of you are, as I am, old enough to remember when we had Gravitations on our TV, right? So when you get a very poor signal, you have all that static in the background, and you can kind of see the TV signal. And when you have a really strong signal, the static goes away. So that's the game in experiments. There are things that produce things that aren't signals, and our job as experimental physicists is to reduce that static, that noise, as small as possible, so that we can detect the gravitational wave. And so at LIGO, they're very, very good at this, and it took them 15 years to build the experiment to make sure we knew it wasn't things like the wind. Actually, what's a bigger problem is like cars driving by on the freeway, right? Undergraduates bouncing basketballs, all kinds of stuff. Okay, that's a good question. Okay, so this is the game. Okay, so I've been telling you about LIGO. LIGO, there is a network of these around the world now. Okay, there's one in Europe called Virgo. There's one in Japan called Kagra. They are our partners. There is an identical one to LIGO being built in India, and it will be online in the next 2 or 3 years. Okay, so very soon there will be a network of 5 of these around the globe. But the 2 in the United States are called LIGO, the Laser Interferometer. That's what they are. They're laser interferometers. That's what we're using to measure the distances. Gravitational wave observatories. There's astronomical observatories. There's one in Hanford, Washington, okay, and there's one in Livingston, Louisiana. Okay, so these were chosen and the sites were built. They've been there for about 20 years now. We have done a series of engineering runs, and right now they are down. They are opened up. I'm going next week, actually. They are replacing optics and fixing wires and doing stuff like that. So we're in the middle of what we call our 4th observing run. Okay. So there's very different problems. If you go visit, both of them have a visitor center. So if you go visit, you can certainly stop and visit. In Livingston, you can see they're in the southern forest there. And so it's very wet in Louisiana. So when they dug up the berm to put the interferometer on, it filled in with water. Okay? And so in Louisiana, things live in the water. So you have to be careful when you go out at night because there's gators and stuff like that. In Hanford, we have things like rattlesnakes and stuff like that. But the big problem in Hanford is we're on the edge of the nuclear reservation. So the tumbleweeds blow across and they bundle up against the arm of LIGO, but they came from the nuclear reservation. So you have to treat them like they came from the nuclear reservation. Right? So we have different kinds of problems. I think in both places people shoot at the observatory. That's what people do. So they have big concrete tubes over the interferometer, so you can't hurt it. So anyway, okay. So if you and this is inside. This is our so-called injection optic. So that's where the laser goes into the instrument, and then it flies up and down these 4-kilometer arms. There's a mirror at the end. That's one of our rocks, and there's a mirror here where the laser comes in. That's one of our other rocks, and we're measuring the distances along the arms. Okay? Okay. So if you get to go inside, oh, this is what it looks like built out of Lego. I built these, I showed these at a Lego convention. They're like, they really, that's not a very good model. And then you show them this, they're like, oh my gosh, it looks really like Lego. If you get to visit, right, they do tours once a month. And they have a lot of this on display, but if you work, you get to go inside. So this is inside here. So the lasers come into the system, and then there's these 1-meter diameter beam tubes that go out the 4 kilometers. And the precision to which they are level is like a millimeter over 4 kilometers. Okay, they were spiral welded as a single piece. So Chicago Bridge and Iron Works came out and did it. And it is the largest vacuum system in the world because we have to have all the air out of the tube because the laser will hit particles of dust and stuff and cause noise that interferes with the gravitational wave function. Okay, so this is a mammoth scientific enterprise. You can see the lasers here. This is the beam tube with the concrete cover on. This is my favorite thing there. So this is one of the baffles between the laser injection and the tube. So you'll see there are these big clamps. So they take a big mechanical arm and they pinch it and they crush these baffles and they can take it out and stick it back in. But this is here because it's out in the middle of the sunshine, and so the tube heats up and then it expands and then it cools down and it shrinks, and so that baffle takes up the heat and shrink. Right? That's why you need engineers to help you with this stuff. They're like, this is going to be a problem. They're like, really? Yeah. They're like, yeah, really. Okay, so there's all kinds of cool little things like this that they'll tell you about. So I mostly work on LISA. So LISA is to do this thing in space. We have 3 spacecraft that are shining lasers back and forth between each other over 2.5 million kilometers. So they're not connected. Okay, and so NASA doesn't let you build these sorts of things unless you prove you can do it. So we flew a mission called LISA Pathfinder to show that we could, have little rocks floating in space and monitor where they are with lasers. Okay, so our rocks are these little cubes of gold and platinum. They weigh about 2 kilograms. They cost like 10 million euros or something. Okay, so they don't let people like me and you touch them. Okay, because we get fingerprints on them, we lick them. So this is a tungsten analog. Okay, because tungsten weighs exactly the same, 98% exactly the same as the gold and platinum that we make the real ones out of. So they made these ones out of tungsten because they cost like $400, and then they let us hold them, right? Okay. So some of you may have seen this. I brought this with me last year and passed it around. Did anyone hold it last year? Yeah, a few of you. Okay. So the reason I have that cube is because they showed it to us at a meeting, and I said, "Can I borrow it? Because I'm going to give a public lecture." And they're like, "Sure, just bring it back." And so I went and gave more than one public lecture, as you have heard I do. And then when I brought it back to them, they're like, "Oh, what have you done with this?" And I'm like, "I've handed this to 3,000 people." And they're like, "Well, you just keep the cube." So I have the cube. I brought it again. Do you all want to see it? Yeah, okay. So the cube is very famous. It goes around the world. And if you are so inclined, I collect pictures of people with the cube. So there's my email address, and I can add you to my big pile of pictures of people with the cube. NASA loves that. It's very helpful in trying days for this space agency. So you can see here, this is what we mean when we say rock. Okay, it's basically a mirror, and the whole point is you'll see it's heavy and it responds to gravity, and I can monitor where it is by bouncing a laser beam off of it. Okay. Some of you will ask about the little holes. That's because you'll see you can't just put this on a rocket, throw it into space, and vibrate all over and destroy everything. So you have to clamp it down. And then the little holes kind of push it out to the middle of the spacecraft and let it go so that we know where it is. Okay?
It's free floating.
It's free floating. It doesn't touch anything. The spacecraft's job is to protect it from anything that might hurt, like solar wind, cosmic rays, whatever. Yeah. So it's free floating in the spacecraft. Very cool. Okay? Okay, so that's the cube. Okay, so this is the game, right? The technology arrived. at a very opportune time in my career when I was in graduate school. And so I went to graduate school to study black holes, and I'm like, oh, well, I can study black holes and do astronomy with them, right? So now we do gravitational wave astronomy. So let me tell you.
Quick question.
Yes.
Over
Sorry.
here.
Yes.
Why did you pick a cube versus some other geometric shape?
So this is a point of contention. If you have friends from Stanford, they're like, they really should use a sphere. Okay,
That's what I was thinking.
So we ask about this, there are different problems using a sphere versus using a cube. And so for the sphere, with the cube, we absolutely know where we're looking at because there's flat sides. With the sphere, we have to put registration marks on the cube. And so you have to not only reflect off the cube, but you have to see the registration marks so you know how it's oriented and if it's spinning. And so there's kind of different problems. And I would say there's no right solution to every problem. There's just different solutions. But our colleagues at Stanford, I think, would really think we should use a sphere. And so this will not be the first gravitational wave observatory in space. And sometime before you and I are old, they will almost certainly build one with a sphere. Okay.
I'm mystified how you can hit that little tiny target
Mm-hmm.
over all that many
Over 2.5 million kilometers, yeah. So we send out a laser beam. The telescope on LISA is about 30 centimeters, so it's the size of an amateur telescope. For the amateurs in the audience, it's something like f1.1, so it's very, very fast telescope. But it goes out through a telescope, so the initial output beam is about 30 centimeters across. But it spreads out and is about 10 kilometers across when it gets to the distant spacecraft. And so there's kind of two things we have to do. We have to make sure we hit the spacecraft, but it takes 8.5 seconds for the light to get there. So those of you who are hunters know this. We have to point to where the spacecraft is going to be in 8.5 seconds. But it's a big enough spot that we can do it. And so in addition to the telescope, there's what we call star trackers. So they look at all the stars, and then they do the internal calculations, say the spacecraft should be there, and then they shoot the laser.
So this thing is in our solar system.
Yeah, so LISA, I don't have a movie of it. LISA will be behind the Earth and follow the Earth around the sun. Yeah. Okay?
It's orbiting here.
It's orbiting the sun in the Earth's orbit. Yeah, so the Earth goes along, and then you kind of wait a little while, and LISA will be chasing it. Yeah. Okay. Okay? Everyone good? Okay. So let's look at our plot that I promised you we would look at. Okay? On September 13th, question?
Can we see LISA on our ax, our star ax?
Ah, yes. So LISA has not flown yet. So we just, it's been funded now by the Europeans and NASA. We'll see what happens with NASA. They just announced the engineering, the aerospace firm at the Paris Air Show that's going to build it. And so they will start building next year. It will take us about 10 years to build it, all three spacecraft. Okay, so 2030, when I come back in 2034, I'll have the first LISA data. Okay? Okay, 2034 data, did you hear that? Okay.
One question. It seems like it would be very difficult to calibrate the distance between the spacecraft to make sure that they're exactly stationary in relation to each other.
Yep. So on LIGO, we absolutely depend on knowing exactly what the distance down the arms is. In LISA, we have to do a special kind of measurement. So whoever it was asked me about the laser, right? So the laser goes out and it's 10 kilometers across, but we don't receive enough laser light that we can bounce it back and send it back to the original spacecraft. So what we do is we measure the properties of the received laser light, we lock a new laser to it, and we send a new laser signal back. So we have this kind of very different ability to understand what the laser's doing at every place in the spacecraft constellation. And so we synthesize paths that aren't just down an arm and back. What we do is we synthesize a path that goes down the arm, and down this arm. So it goes down both arms. And what that does is that gives us a very precise measurement of what the spacecraft separations are. So we call that digital interferometry or time delay interferometry.
So is that going to be like microthrusters to try to adjust the distance, or
So
or
they
just whatever happens to be the
Yeah, so we have Newton microthrusters that keep the spacecraft centered on the cubes. But wherever the cubes go, we follow them because gravity is the only thing that's supposed to be pushing them around. So, yeah. But we've done this in the lab. So the guys at Florida have 25 kilometers of optical fiber that they've done this time delay interferometry through, and it absolutely calibrates the way we expect it to. So, okay. So, okay. One more question, then we'll go.
You have to worry about asteroidal debris. Is it following the Earth?
Yeah. So we've written several papers, my group, we've written a paper about dust flying by LISA and causing gravitational perturbations, so noise, to answer this gentleman's question in the front. So if a small rock flies by LISA, it will perturb it, but the way we distinguish is it only happens at one satellite, not at multiple ones. So we can tell it's not a gravitational wave. We are currently doing a study, so we're almost done with it, where we want to know, can you use LISA to detect near-Earth asteroids? Because this is a big problem. We don't know of all of them, and LISA will be very sensitive. So we're working on that right now. Okay? Okay. So, I promised you we'd look at this plot. On September 13th, 2015, this is everything we knew about neutron stars and black holes in the Milky Way galaxy. Okay, so what should you know about this plot? All the neutron stars exist down here in this range of 1 to 2 solar masses. Okay, and there are, I don't know, like 80 of them or something. Okay? All the black holes exist in that range of 5 solar masses to 20 solar masses. And there are not very many of them. There's 20 of them or so. Okay? So, the reason I told you about September 15th is, okay. And then in particular, there's a gap there. Okay, we've never seen an object between 2 and 5 solar masses that was dead. We see stars, but we don't see neutron stars or black holes, dead remnants. Okay? And a lot of that we felt like we understood, because we kind of have this classic picture about the way stars are born and die, right? So stars are born out of gas and dust in the Milky Way, out of nebular material. Average stars like the sun, they form, they spend their lives burning hydrogen into helium, they eventually become a red giant, they eventually slough off their atmosphere, become a planetary nebula, something the amateur astronomers can show you, and then in their core become something called a white dwarf, a stellar remnant, a skeleton about the size of the Earth. Okay, LISA cares a lot about these. Okay, I'm not going to talk about those. This is the side that LIGO cares about, because if the star is much bigger than the sun, it also spends its life burning hydrogen into helium. It becomes a red giant, or red supergiant, but then it explodes. A supernova explosion. And that explosion throws material out into the universe. It makes those nebulas that we showed on that very first slide. But the skeletons are these very compact objects. Neutron stars, which are about the size of a city, okay, or black holes, which are about the size of sisters. Okay? So, everything depends on the mass of the star. Only giant stars, giant enough stars, can explode to create these neutron stars and black holes. Okay? And if we counted all the ones on that plot, that kind of told us something about what the history of stellar evolution in the Milky Way was like. So if you look at astronomical history, we kind of spend all of our time looking for these stellar explosions, okay, these supernovas. The explosion will momentarily outshine its parent galaxy. When the Crab supernova went off, you could see it during the daytime and read by it at night. Okay, so they are extraordinarily bright. Okay, they leave behind these spectacular remnants, and in the center is where that stellar skeleton is. And in the Milky Way, we've seen several of these, or many of these. Okay, there's about 2,000 total pulsars known, and there's kind of 100 or so binary pulsars. So in the context, right, when you have a star in about 8 to the 15 solar mass range, we don't know that number exactly. Okay, because we haven't seen enough of them. And because try as we might to simulate these on computers, we're still not very good at it. So we don't exactly know all the details of how it happens. But somewhere in this range of 18 to 15 solar masses, it's heavy enough that it can explode. Okay, and that neutron star, as we said, right, is kind of the size of a small city. So if I stuck it down here on top of Sisters, it would kind of reach halfway out to, what is it, Black Butte out there, right? Okay? If I increase that, so that's called the neutron star. If I increase that mass to 15 to 40 solar masses, okay, so these are about the heaviest stars. There are a few stars we know they're heavier than that, but kind of 40, 50, 60 solar masses is the most massive star we've seen. Okay, we think there could be heavier ones. We haven't seen them yet. Okay, these stars, when they explode, the explosion is so strong it will crush even a neutron star. And when it crushes that neutron star, the gravity becomes so intense that the neutron star itself collapses to become what you and I call a black hole. So if I could just squeeze on that neutron star a little bit and shrink it down just to barely bigger than Sisters, you would have a black hole. Okay? But the size of that black hole is completely limited by the size of the star that made it. And up until September 13th, 2015, the biggest black hole we'd ever seen was 20 solar masses. Okay? And that agreed well with our understanding of what it takes to make it from a star in the Milky Way today. Okay?
Question.
Yes?
So when you say the size of that black hole sphere, are you talking about the event horizon?
Yeah.
Yeah.
So what I'm showing you is the size of the event horizon.
Gotcha.
Yeah, so I'm not going to give you the whole black hole talk, but the quote-unquote surface of the black hole we call the event horizon. It's not a solid surface, but it's the point where the gravity becomes so strong that you ain't getting away if you go in. Okay, that's the place where it requires to go faster than the speed of light to get away. Okay, gravity gets stronger as you get closer. So, one more question.
Isn't like time 16, like the Phoenix something black hole way bigger than solar masses?
Yeah, so there are bigger black holes than this in the centers of galaxies. So in particular here in the Milky Way, there's one called Sagittarius A star, and it weighs 4 million solar masses. Okay, so what I'm saying here, these are what we call stellar origin black holes. They're black holes that come from stars, not from other processes in the universe. Okay, so those big giant ones come from other things than stars. Okay? Okay, and LISA will study those big giant ones. So if I give you guys the LISA songs again. Okay, so September 14, 2015. I was moving into my house in Chicago this day. As my wife says, the laptop came out on a box, and the boxes never got unpacked. Until we moved to New York. Okay? There are worse reasons for boxes to not get unpacked. Okay. On that day, at about 4 o'clock, 4:30 in the morning, LIGO made the first completely unexpected detection. We thought we were reaching the range where we were going to make detections, but I mean, we basically had flipped the switch and like, oh, right? There's this story that we took the signal in and showed it to Kip, and Kip Thorne, who's our kind of master of gravitational waves. I was a postdoc in his group at Caltech. And they showed it to Kip, and Kip's like, oh, well, we've discovered that. Right? He's just like, oh yeah, this is what we've been predicting for 40 years, right? Okay, so what did we see? We saw 2 black holes going around each other. One of them was 29 times the mass of the sun, and the other one was 36 times the mass of the sun. They were going around each other let's see, so that was at 40 times a second, I think it was. Okay? And the whole thing is 1.4 billion light years away. Okay? And so for 2.5 seconds, we saw the gravitational wave signal, and then it vanished. Because the black holes were moving around each other, so the gravity was changing, but then they merged and formed a single black hole, and the gravity stopped changing. So the gravitational waves happen when stuff's going on, and they end when stuff stops happening. Okay?
So it took 2.5 seconds for the black holes to
From the time LIGO saw it till the time it ended. Okay? So, let me show you what our data looks like. Okay? So what you were just seeing was a visualization, a pure simulation of the event. Okay? This is what our actual gravitational wave data looks like. And if you're an engineer or a scientist, you're used to looking at graphs like this. Okay? So what are you looking at? So this here is the actual gravitational waveform of the black holes. Okay? That is the separation between the mirrors in LIGO getting bigger and smaller. In the background, this is what we call a spectrogram. Okay? So time goes this way, and along here are frequencies. And many of you have seen these before. They're on your stereo. When your music plays, right, the little lights that go up and down, it tells you how much low frequency is, how much mid frequency, how much high frequency. So what you see for gravitational waves is that early on in the signal, there's low frequencies, like bass signals. And then over time, the frequency gets higher and higher and higher until at the very end, it's very high frequencies. So if you were watching those little things on your stereo, you would see it on the left side, and it would slowly die down and increase on the right side. Okay, so that's what that plot's showing. Okay, so we call that a chirp. And the reason we call that a chirp is because these are actually at frequencies that your ear could hear. Your phone has a whole bunch of wiggles on it that when you push those wiggles out through the headphone jack, it plays Glenn Miller or AC/DC or Taylor Swift or whatever it is you listen to, right? But if I steal your phone and I take all your Taylor Swift off your phone and I put my gravitational wave data on it, when you push it out through the headphone jack, you can hear it. Because it's just wiggles, just like the Taylor Swift, right? Okay, so I'm going to play that for you. Okay, so this is going to play over just a half a second, the half a second where it's loud enough for your ear to hear. Okay, and you're going to hear the gravitational wave data turned in audio. Okay, so why do I do that? Because when I send this to the editor of the Chicago Tribune, right, they're like used to Hubble pictures. They're like, oh wait, get your boxes, right? So you got to give them something to kind of say, oh, this is cool, right? So this is cool. Okay, so I'm going to play this. It's going to play twice. It'll play it once at the actual audio frequencies, and then it'll play it again, pushed up an octave higher, so it's a little bit easier for your ear to figure it out. Okay? The thump is the black holes merging and the gravitational waves ending. And you hear that chirp? That's why we call it a chirp. It sounds like a parakeet barking, right? Okay? So that's what our data sounds like. And we do this all the time. We take our data and we push it out. And sometimes your ear is much easier to train to hear this data sometimes than the computer. Computers are really hard to teach to do this stuff. Okay? But we had a whole project for a long time where people just listened to the data all the time, right? It's kind of cool. Okay, so this is how, on September 14th, the graph changed. And the thing you should notice is that the one gravitational wave detection adds 3 black holes to the plot. The 2 that created the final black hole. And all 3 of them are more massive than any black hole we had ever seen before. This was 10 years ago. We still don't know how the universe makes these kinds of black holes. Right, wow, okay? We have some ideas. We have, LISA will play a role when LISA flies, but we don't know enough yet. We can't figure out how the universe makes these kinds of black holes, okay? And it gets worse, as you said. Okay.
Didn't you say that the black holes are created by the massive stars that explode?
Right,
So,
but the biggest star you and I have seen is about 40 solar masses. And when we blow up a 40 solar mass black hole, we think the biggest black hole can make its 20 solar masses.
oh, I see. You don't know how those big ones got.
We don't know how we make these big ones. Okay. Some of us think we know, but we don't know.
So we talk of singularities where
Yep.
the equations go to infinity and gravitational attraction goes to infinity. So how can 2 black holes possibly ever merge? Wouldn't they just keep circling each other faster and faster?
Yeah.
And
So-
if the speed of light is
Yeah.
a limit, then how does they're circling each other
Yeah.
interact with the speed of light?
Yeah. So there's a lot of weird things that happen around black holes, and those of you who have studied black holes have probably read about some of this. The initial difficulty with black holes was how do you even form black holes from stars collapsing? Because time gets very distorted near black holes, and in fact, when they were originally written down, the Russians called these things frozen stars, because it looks like the material never actually collapses beyond the event horizon. And so if you kind of extend those ideas, the same thing would happen, the black holes would never actually merge, because time gets so warped near the black holes. If you put yourself, as we say, in the frame of reference of the black holes, if you travel with the black holes, the time does not become that distorted, and they actually do merge. And so all of the weird effects that with the distorted time are basically, I don't want to say hidden, they are suppressed from our view, because when they get to that point, there's a redshift. It's a gravitational redshift. It's so extreme from the places where those black holes merge that we can't see the data anymore. But as far as we're concerned, the black holes are together in such a small space, they look like a single object. And if we do the relativity in the frame of them, they become a single object. So, okay. So that's a subtle and difficult question to fully answer. So, okay. Okay? Okay, one more and then we're going to go on.
The black hole has infinite mass and zero volume. And how can black holes be bigger or smaller?
Right. So this is related to the question that Mel was just asking.
Yeah, how can they be bigger or smaller?
Right. So the question is if they have zero volume, and so they don't have infinite mass, they have what we call infinite density, which is the mass and the volume together, right? The amount of gravity is what we are calling the mass of the black hole, because you and I living outside the black hole can measure the gravity of it. And when we say the black hole has this mass, we're saying, if I just write down the physics formulas, how much mass do I need to make the gravity as strong as I measure it out here? This point in the center that we were just talking about, called the singularity, is actually beyond our understanding in the context of physics, right? It means, as physicists, we think it means there's bits of physics that we don't understand exactly what happens down in the center of the black hole. And so that's for future physicists. It sounds like we're going to be a black hole physicist. It sounds like what future physicists will have to figure out. Okay? That's a hard question.
But how can there be if there's any mass with zero volume, then it's going to be infinite mass?
It's infinite density.
Yeah, infinite density.
Yeah.
So how can it get any density?
Yep, that's the problem. Physics doesn't work. That's what we mean. That's exactly what we mean. That's the problem. Okay? Okay, we can talk some more about it after. Okay. Okay, one more.
Is the singularity and event horizon the same?
The event horizon is the curtain behind which the singularity hides. Yeah. Okay, the singularity is in the middle of the black hole. Okay, the event horizon is the shroud on the outside.
And that's what we see.
And yes. It's the thing we're detecting, is the event horizon. Yeah. C is a hard word. We use it as a structure. That's how we're doing it. Yeah. So. Okay, let me tell you about the second event. So the funny story about this event is I was at Astrocon in Casper. So the way these are numbered, GW means gravitational wave. The first number is the year, 17, so this is 2017. Second number is the month, that's August. The last number is the day, 17. What was happening on August 17th in 2017? Total solar eclipse, right? So I was in Casper, Wyoming, giving a talk about the first detection. And my phone was going off because we had made this detection, okay? And we keep everything totally secret when we discover it, okay? Or at least we did then, because these were all, so everyone thought I was really excited because I was talking about the first detection. I'm like, holy crap, what's going on? Because my phone was going off, okay? So let me tell you about this detection. Okay, so GW 1708, right, we were all watching the eclipse. But the thing that happened is we made the detection in LIGO. But at the same time, our partners who work on the Fermi Gamma Ray satellite also saw a signal. Okay? So this is what our data looks like. Here's that chirp, okay, that LIGO saw. Okay, so you'll see it's very, very long. It's like 40 seconds long. Okay? So this tells us right away that it's not a pair of black holes. It's neutron stars. So these were the first neutron stars we had detected. Okay? So we saw the merger. Here's the zero mark. This is when LIGO saw the merger. And 1.7 seconds, this is what gamma ray astronomers do. They just watch. They're like, oh yeah, 1,000 gamma rays. Oh, 875 gamma rays. Oh, 1,100 gamma rays. This is all great. They just count gamma rays all day. And then they saw this jump up to more than 1,500 gamma rays. And they're like, holy crap, 1,500 gamma rays. Okay, so they call this a gamma ray burst. Okay, and for 40 years, we have not known what gamma ray bursts are. But here's one that went off within 1.7 seconds of a gravitational wave event that we knew was neutron stars. Okay, so this mobilized, the reason my phone was going off, 4,000 astronomers around the planet started looking for this thing. Okay, and the paper we wrote, this is the largest scientific paper written by astronomers, there's 4,000 authors on it, okay, about this discovery. Okay, this is how important it was. Okay, and so what's going on? So this is what's called a short gamma ray burst. So there are two neutron stars that are initially going around each other. Okay, and in this phase, they're emitting gravitational waves. They're way down on that slope, that 40-second slope that you can see. They're going around each other, 40 times a second, just going faster and faster and faster as they get closer and closer together. As they get closer and closer together, the gravitational interaction gets stronger, so the gravitational waves get stronger. That's why that chirp begins to happen. And then, as they get even closer together, they begin to see each other's gravity, and they begin to distort. And you can see that in the gravitational wave data. It allows us to measure the shape of the neutron stars. But eventually, they get so close together, they begin stripping matter off of one another. They collide, and when that happens, they explode. And when that explosion happens, it creates the short burst of gamma rays, and then it creates a very bright point of light and an expanding shell of material that's decaying radioactively that we call a kilonova. A kilonova. So like a supernova, but weaker. Okay? So, this is what the astronomers were looking for. So it happened during the daytime, and so we had to wait for sunset for every telescope on the planet, and we knew where LIGO thought it was in the sky, okay, and every telescope went looking for it, and they found it 11 hours after Fermi did. Okay, and so this is what it looks like. Okay, it's in a galaxy, which some of my amateur astronomer friends have probably seen. Okay, it's called NGC 4993. I went and looked at my notes. I've seen this galaxy. My notes say it's a small, dim, fuzzy blob. Okay? But, right there on the side of it was a new star, a kilonova. Okay? So this was, as we say, the first multi-messenger detection of a gravitational wave source. We detected it both in gravitational waves and in light. And this has been the holy grail of gravitational waves forever, because you can learn tons of things because gravitational waves and light give you very complementary information. Gravitational waves told us it was neutron stars, it gave us the masses, it gave us the sizes, but then the light told us the energy that went into the production of elements, it gave us the origin of the gamma ray burst, right? All kinds of things come about from combining the two things. Okay? So, this is where we were at the moment we made that detection. Okay, so you can see these purple ones were all the black holes that were known, all these yellow ones were the neutron stars were known. We had made several other black hole detections, which you can see there at the time. But right here, this is the two neutron stars, and they merged into something that's right in the middle of the mass scale. And you know what? We have no freaking idea what it is. So most people think it's a black hole. Just to be honorary and contrary, I think it's a supermassive neutron star. Okay? But we don't know what it is. Because the moment they merge, the gravitational waves end. But we can still see it in radio waves. So they're still monitoring this now, 7 years later, 8 years later, and they can still see it in radio waves. So maybe we'll figure it out, maybe we won't. But it's very interesting that it's right here in this area we call NASA, where we've never seen anything before, right? That's awesome.
Do we think the mass of it is not equal to the sum of the two masses?
Oh, yeah, so if I haven't told you everything, but for the black holes, the final black hole mass is not the sum of the initial two masses.
Right.
Because energy goes into the gravitational waves. And in this case, it's energy in the gravitational waves and in the shell that it shed. Yeah. And so measuring the shell has been a massive enterprise. And the thing it has led to is kind of a new understanding of the periodic table. So you've all heard Carl say for 40 years that you and I are made of star stuff, right? But if you go talk to the astrochemists, they're like, yeah, we're made of star stuff, but we can't make all the star stuff in the quantities we see from supernovas. Where is all this stuff coming from? But now that we've seen merging neutron stars, all these heavy elements in purple here, we know how much of that comes from merging neutron stars. So finally, at last, the amount of star stuff and the quantities we see, we're beginning to get the full picture. Right? So what this really changed more than anything else is astrochemistry. You really are made of star stuff, as is the gold in your ring, and the uranium in the planet, all that stuff comes from, right? Uranium is fully purple. This is how you get uranium. You collide neutron stars. And there's uranium on Earth, which means some of the stuff that went into the solar system came from colliding neutron stars. Isn't that cool? Okay. Okay? So this is, as Carl said in Cosmos, right? We're all star stuff. Okay? But now, finally, we kind of think we have the picture. Okay, let me tell you one last thing, and then we'll end. We've been taking a little bit of questions. So this is where all of us get. So most of us will agree, the first detection, the first multi-messenger detection, those are the things, man. Those were so cool. 4,000 astronomers writing papers, Nobel Prize for the first discovery, right? This is what it's all about. Okay? But then it's like, what's the next most important thing? Okay? And until we detect a supernova in gravitational waves, we're going to argue. Okay? But this one, I think, is probably the most important. Okay? Because it really changes that mass clock you and I have been looking at. So this is GW 1905-21. So this is May 21st, 2019. Okay? So this is the year before the pandemic. And we saw two black holes merge to form a third black hole. It's a LIGO story. But every single one of those black holes was bigger than any black hole we had ever seen before. Every single one. It's this first story all over again. But look how heavy these are. Okay? 66 and 85 solar masses merging to make 142 solar masses. Okay? Now for astronomers, these really stand out because these 66 and 85, these lie in a mass range where we think it is impossible to make black holes via supernova explosion. There's something called a pair instability. When stars get too big and they collapse, all of the atoms disintegrate and they start creating electrons and positrons. So positrons are the antimatter component that matches electrons. But they annihilate each other. And what that does is it destabilizes the collapse, so the core can't form a black hole. Okay, so these are called pair instability gaps. And so we've never seen, or we thought you'd never be able to see black holes like this. But here we are, two black holes in the pair instability gap, and we have no idea how the universe created them. Okay? And if we believe the pair instability, that you can't make these black holes via explosion, what that means is these two black holes probably came from a previous generation of big black holes, like the ones that we've been seeing already. Okay? Now that's a hint, because that means if it came from black holes, those black holes have to find each other, which means they have to form in dense environments. They can't just form over there and one over there, because they're never going to find each other. You have to form them over there, and then they have neighbors, and that would be neighbors who burn and form. Right? So these are the games we have to play. What does the clues tell us? And this suggests they're from dense environments, which is good for us LISA folks, because our ideas about where these come from are from dense environments. Okay? So we'll solve this mystery in the next 10 or 20 years, I'm sure. Now, I'm going to pick a bone with my LIGO colleagues. Okay? This is an important black hole because it's 150 solar masses. Okay? But they have taken to calling it an IMBH, an intermediate mass black hole. Okay? So I answered a question earlier for our future black hole physicists here in the front row about big black holes in the centers of galaxies, right? So we've long thought that for small galaxies, like dwarf galaxies and other clusters, there should be small giant black holes that we call intermediate mass black holes. 1,000 solar masses, 5,000 solar masses. And so LIGO calling these intermediate black holes kind of rubs us galaxy people the wrong way because they're too light to be intermediate mass black holes. So we've started calling these light intermediate mass black holes. Okay. But nonetheless, this is important because the only way, there is no known stellar process to make black holes this size. Okay, so this has to come from the merger of black holes. Okay, so we're slowly filling in all of these masses of black holes, and we're seeing them. We absolutely see them. We know their masses, but we don't know how the universe makes it. Well, we know how it makes these. It makes these by making these, but we don't know how it makes those. And it might make those from these, but we don't know how to make these either. Right? That's kind of the way it goes. Okay. So what's the catalog look like today? If you go to the site at Sierra, this is what the stellar graveyard looks like today. Okay, it will look this way for another, I don't know when the paper's going to come out. It's been this way for a few years. We're about to release a new catalog, which I think doubles the number of black holes on this one.
What do the lines mean?
Oh, so as the plot has become denser, we have to show all the black holes, the 3 black holes that come from a gravitational wave event. So the arrows now, instead of kind of doing this, they point through each other to the final black hole. So that was my contribution to the plot. They're like, how are we going to get all this data on here? Just make the line straight. That's okay. Yeah. Okay, so this is what it looks like. You see we've detected a few more neutron stars. You'll see there's a few things appearing in the mass gap here. Okay, and you see those really heavy ones up there over 100 solar masses, and we've seen a couple of those. Okay, so lots of mysteries, lots of black holes that we don't know about, and that we wouldn't know about unless we had figured out to do what Einstein thought was impossible. Right? So it's kind of cool. So the outstanding mystery, as I've said, is what are, as we say in the biz, what are the formation channels? Where are these black holes coming from? How do you make them? And there's lots of different ideas, and the ways we're working on that is binary stars. That's what my group actually works on. We simulate binary systems on the computer over their whole life. So we try and create these things on the computer, and then when it makes pairs of black holes, we try and evolve them into the future. So that's what we work on. And then this question here is really the big question, is if you make all these black holes, can they find each other again so that they can make even bigger black holes? And that's a little bit of a problem. We're not quite sure how to do that. We have some ideas, but it's hard to make as many as we're seeing. So the universe is doing, as it always is, something weird, right? Okay, so in the end, it's always about people. I always like to remind people, LIGO is, and LISA, everything you hear about is a huge enterprise. There are thousands of people who work on this. It's not just folks like me, right? We cannot do this without our electrical engineers, with our computer people, without the guys who do the spiral welding. You know, when NASA builds a space telescope, they don't put $1 billion on the side of a rocket and launch it into space, right? They're paying people to mine titanium, they're paying truck drivers to carry rocket fuel, right? All of that money goes into this business, and we can't do it without everyone. You only hear about people like me, people like Kip, but really it takes all of those folks to make this happen. And all of these are our colleagues at LIGO doing all sorts of stuff. Not all of them are scientists, but every one of them contributes to the game. So, okay, so here's a little bit of reading for you. There's a couple of books about gravitational waves themselves. So this one by Brian Clegg and this one by Gilbert Schilling. I like a lot. There are more and more starting to appear, so you'll hear about them. This is a fantastic book by Marcia Bartusiak. Some of you may know Marcia. She's a very good science writer. That's a second edition of the book that she revised after the first detection. So make sure you get the second edition if you want to read about the first detection. Kip's book about black holes and time warps is still kind of, I think, just about the best introduction to all this relativity, space-time curvature, gravitational wave stuff that you can find. And then there's a few websites there for you to look at. Okay? So I will say thank you, and we've been taking questions, but I'll leave it to my host to decide when we should quit, and I'll talk to everyone again for a little while longer. So. Take a few questions?
Yeah, we have.
Okay. I don't know who's first, so let's start here. Yeah.
So light behaves sometimes like a wave, sometimes like a particle.
Yep.
Is the same thing true for gravity?
So the question is, light behaves like a wave and a particle. Is the same thing true of gravity? Okay, so the assumption is yes. Okay, so it's more than light. One of the great discoveries by a physicist named Louis de Broglie in 1923 or 4, he got the Nobel Prize right for his PhD thesis or something, right? He's like, everything behaves like a wave or a particle. And so this is kind of a central tenet, I would say, in modern theoretical physics. And right now, the assumption is this will be true in gravitation, but the only physical theory for which we don't have a quantum theory is gravity. And so we do calculations and we do experiments assuming that there are quantum gravitational particles, what we call a graviton, but we don't have the theory yet. So I think the bias of physicists is yes, but the reality is we don't know because we aren't done. Okay, that's a good question. Yes, and then I'll work my way this way. So whoever had their hands up, make sure you raise them.
Yeah, my understanding is that gravitational waves not only warp space, but also time.
Yes.
And is there any interest in studying the disturbing of time?
Yeah. Yeah, so at the level that we can measure them right now, it's far easier for us to measure the distortion of space, and at the order of the mathematical equations we use, we do not see the distortion of time. Okay? Time absolutely is distorted by gravity. It's kind of central to technology like GPS, but it's not important yet in gravitational wave experiments. Okay? That's a good question. Okay, I saw a hand over here. Yes, and then did you have one too?
A different kind of topic. The current administration.
Oh, now we're going to talk about politics. Okay, yeah, okay.
This is a more practical side.
Yeah.
It comes to NASA and research funding.
Yep.
How does that affect you?
So as a university professor, the place where it will impact me the most is the way we train the next generation of scientists is we fund them through our research awards. So I write a proposal to NASA or the National Science Foundation. I promise them that what I propose to study is, in my case, the gravitational influence of relativity on the evolution of white dwarf stars. And so I propose a set of projects. They give me funding. Almost all of that funding pays for my graduate students to study physics and learn how to do the kind of science we do, which is not just astrophysics, but it's astrophysics, it's high-performance computing, it's data analysis and statistics, and not work at Costco at the same time. Okay? And so then my graduate students, when they graduate, some fraction of them become professors. So one of my graduate students has become a professor. Some fraction of them will go work for the federal government. So one of my graduate students works at NASA now. He leads the LISA data analysis effort. And then my other students end up in industry. So I have a student who works at Google. I have a student who's become a lawyer. She works in scientific law. And so they do all sorts of different things. But it's the training of technical minds in our society that would, at least from my science, that is going to be impacted the most for people like me. So, now there are other questions, right? If you decimate NASA, what does that do to the aerospace industry? That's a big question, right? And that's a big big sector of the economy. So there's other questions. So.
Why are you here?
Yeah, so the Sister Science Club is hosting me here, but, so I just got quizzed on this actually. So I had the good fortune of being sat down in front of Carl Sagan at the right time in my life. I was probably this guy's age, and my parents sat me down in front of Cosmos. And I learned very rapidly early on that it was important to talk about science to people who weren't scientists. And so I have spent my entire scientific career with the personal ethos that it is as much my responsibility to teach science in front of the classroom as it is to teach science in front of the public. And the reason for that is because most of you have not been in the classroom in 40 or 50 years. Okay? But if you think about the world 40 or 50 years, we didn't have iPhones, we didn't have the internet, we didn't have freaking computers, right? The world changes, right? And if you aren't sitting with someone who's immersed in those changes, helping you understand what's going on, how are you ever going to learn it? And so I have always taken the personal viewpoint that I should be out doing this, and so I do. And I came from a little tiny town here in Oregon, and so as much as I can, I come to small places, and I do it because I had the good fortune at the right time of being exposed to a scientist when I was in a little tiny town where we never got exposed to scientists. So that's why. Yeah.
Thank you.
Yeah, thank you.
In the video you showed right at the beginning,
Uh-huh.
is there some significance in, at least in my eye, that the waveforms are moving away from the black hole as opposed to moving towards the black hole?
Yeah. So, okay, so that's a good, the question is, what's the significance of the direction the waves are moving towards or away from the black holes? So what you can't see in that video is the gravitational field is changing dynamically everywhere. And wherever that change occurs, the information about that change propagates away from that point. Okay, and so it propagates in every direction, but what you see in the video is the sum of all the changes wherever you see the light in the video. So in principle, there's absolutely pieces of that gravitational energy that fall into the black holes, and we never see it again. Okay, but it's going this way and it's going this way, and what you and I see is the sum of all that stuff. Okay, that's a good question. Okay, before I go back to our front row question here. Yeah.
How long, if you know, does it take to pump out a 4-kilometer long tube?
Actually, that's a good question. I don't think I know how long it took them to do that. So they had a gigantic spool of steel, you know, it's like this wide, and it's spiraled out, and then they spiral weld it as they go along. And then when they get to the end, they have to bake it. So they put 50,000 kilovolts on it or something, and to get all the gases and everything out of it. But I don't know the full length of time that takes. There's a famous story, I probably have a picture somewhere I can show you at Hanford. It took longer than it was supposed to take. Because the welders, they were, I don't know, 500 meters into it, and they threw down their welding torches, and they're like, we're not going to do any more of this until you tell us what the hell this thing is. Right? Literally, this is a true story, right? And so it just so happened that Ray Weiss, who's the guy who got the Nobel Prize for this, was there at Hanford that day. And so he's like, okay. So there's a picture of Ray in a room like this. They didn't have whiteboards and stuff, but he has one of those big, giant Staples paper pads. And all the welders sitting there in their chaps and their helmets and everything. And Ray explained to them basically what I explained to you, and then they went back to work. So it took a little while to Hanford, but I don't actually know the full time. So, yes, ma'am?
Is there significance on the location of the tube?
So, yeah, so there's a couple of things. So I mean, for practical matters, you have to have a big enough space where you can build it. Okay, so that necessarily means you're not going to build it in the East Coast, because there aren't that many places where there's not going to be towns or roads and stuff. There's obviously politics involved. Hanford was a government facility already, so that was easy. I don't know the story of how they ended up in Louisiana, but you know. The thing about the detectors is you need them far enough apart, because the way we point with LIGO is we triangulate. The signal hits here, and then sometime later it hits here, and that means it can come over there. So they have to be far enough apart. And if you look at the orientation, they're actually oriented the same. And that's because at the time we built them, there was still concern that gravitational waves would be really hard to detect. So we wanted to make sure the detectors were basically doing the same thing. Ideally, we should have one like this and one like this, but we were scared, and so we built them the same. So, okay. The one in Europe gives us really good, and Japan gives us really good triangulation. The one in India will really improve our ability to point at the sky. The absolute best place to put one more is in Australia. And if the Australian, they have had one proposed before, they haven't managed to do it, but that's absolutely the best place you can put one on the planet now to really enhance the network. Okay, let me take one more question and then we'll let folks go. And then you and I will talk some more.
You mentioned that there was no accepted explanation for that intermediate brain black holes. So what are, you said there are some ideas out there. What are some of the pending hypotheses for that?
For where they come from?
Yeah.
Yeah, so those of you who've heard talks about James Webb Space Telescope, one of its primary science missions is to detect light from the first stars. Okay, so the very first stars in the universe are different than the stars that exist today because they were almost pure hydrogen. And when you make stars out of pure hydrogen, they can be much larger than the limits I just told you stars were. It has to do with the kind of light they shed from the atoms that the stars made of. And those those stars could collapse directly to black holes about this size. Okay? Now the problem, so this is the mystery, right? Is we haven't seen the first stars yet. We will. James Webb will figure this out. But the question is, how many of them do that? Because that will tell you something about the numbers of these things in the universe, right? So that's an example of one of the alternatives.
Right, so these would be very old.
Yeah, they would be very old, and they would have persisted. And so then the question is, where do you look for them, right? And so, like the globular clusters are in the stars in the Milky Way, so maybe they're in the globular clusters. But we've looked in the center of globular clusters, and we don't see black holes.
What about galactic centers?
So galactic centers, which I told this gentleman about, so they tend to have big ones. So the bigger the galactic bulge, the bigger the black hole. So like the Milky Way has a 4 million solar mass black hole. M87, which is a giant elliptical galaxy in the Virgo cluster, has a 4 billion solar mass black hole. So they're big, they're not small like these, right? So this is why we look at dwarf galaxies, tiny galaxies, they're smaller than the Milky Way, because if they also have black holes, then they'll have these intermediate mass black holes. Just because there appears to be a relationship between the size of the galaxy and the size of the planet.
Any other hypotheses out
Those are the two I work on the most. So those are probably. So I have a colleague who works on dwarf galaxies, and she has some interesting models that can make them, but not this light. Hers are all kind of 500, 800 solar masses. So I should ask Jillian actually what she thinks of these light ones. Yeah,
So
I have
how
a
small can you go?
You mean what?
In the size of black holes, very small.
Well, right now, LIGO's filled in the masses all the way up to 150. And then I think the next lightest one that we know of with certainty is something like 10 or 15,000. So there's still a big gap to fill in. So, yeah. Okay, I'm going to let everyone go. I'm happy to chat with anyone who wants to. Thank you so much for your attention.